Hello everyone. In this video, I'll go over some of the frequently asked questions in RTL and digital design interviews. One question that is commonly asked is what is the difference between combinational and sequential logic? Let's first understand both these circuit types before diving into the key differences. Combinational logic circuit. Combinational logic circuit is a circuit of interconnected logic gates where the output depends only on the current input values. The output of these circuits is generated by logical combination of the present input values. These circuits do not have a clock and are not affected by the past inputs or the previous outputs. Here is an example Verilog code. Now let's look at sequential circuits. Sequential circuits are digital logic circuits where the output depends not only on the current input but also on the past inputs. In other words, these circuits have memory and they store state or output over time. Here is an example Verilog code. In this example, a flip-flop stores the value of D on the rising edge of the clock. Now, let's put together the differences between combinational and sequential logic circuits. For combinational circuit, the output is purely a function of the present inputs. Whenever the input changes, the output immediately reflects the new values. In contrast, the output of the sequential circuit depends both on the present input and the previous input and outputs. Combinational circuits have no clock. Sequential circuits have a clock. Combinational circuits have no memory element. Sequential circuits are capable of storing the information as it contains memory element. Combinational circuits are fast. The output is generated instantaneously when the input values change, with no delay or dependence on any clock signal. While the state of sequential circuit is typically updated at specific points in time, often at the rising or falling edge of the clock signal. Combinational circuits are easy to design. Sequential circuits have feedback path where the output is fed back into input, enabling them to maintain a state over time and make decision based on the previous states. These circuits are complex to design due to added memory and feedback path. In combinational circuits, the basic building blocks are logic gates, while for sequential circuits, the basic building blocks are flip-flop and latches. Example of combinational circuits are adders, subtractors, multiplexer, demultiplexer, encoder, decoders, etc. While for sequential circuits, we have counters, registers, etc. Another important concept to understand for interviews is clock gating. Clock gating is a widely used technique in digital circuit design for power management. It works by selectively turning off the clock signal to certain parts of the circuit when it is not in use, effectively reducing power consumption. This technique is particularly effective in minimizing dynamic power dissipation, which is the power consumed due to switching activities in digital circuits. By controlling the clock using clock gating technique, designers can avoid unnecessary switching in the idle parts of the circuit, which helps to conserve power. Here is the Verilog code for the clock gating circuit. This block diagram illustrates the logic required to implement clock gating in a digital design. It shows a simple circuit where a logical AND is performed between clock and clock-enabled signals to generate gated clock, gated underscore clock. Although this technique requires a slight increase in hardware, the power savings are significant. In the corresponding waveforms, we can observe that the clock signal is passed to gated underscore clock output only when the clock enabled signal is high or logic 1. To summarize, in order to optimize digital design efficiency, clock gating disables certain parts of the circuit that are idle or not in use. Consequently, the flip-flops in those sections do not switch states, avoiding unnecessary toggling and thereby reducing dynamic power consumption. Let's discuss the benefits and the challenges of implementing a clock gating circuit in the design. First, the benefits. By implementing clock gating technique, the clock signal is only used in the design when it is necessary. It significantly reduces dynamic power consumption, especially in large systems with many idle subblocks. Clock gating technique is scalable. It can be applied at different levels of a system, individual registers, a subblock in a module, entire module, or at a subsystem level. However, there are few considerations to keep in mind when incorporating clock gating circuits in a design. Implementing clock gating circuit in design adds extra logic, which can affect the overall timing of the circuit. Therefore, extra caution is needed to avoid timing violations. Verification engineers must develop a thorough verification plan for clock gated designs, as improper implementation of gating can result in functional failures or reduction in performance. Another key question frequently asked in digital design interviews is the difference between a Verilog task and a function. First, let's understand what each of these constructs represent and how they are used in Verilog. A function in Verilog is a reusable block of code that takes input arguments, performs operation based on given statements, and returns a single value. Here is the syntax. A function begins with keyword function and ends with keyword end function. Input ports are declared after keyword function, and then there are statements. In a function, we can add keyword automatic or static. If a function is automatic, the variables used inside the function are not shared between invocations. These are dynamically allocated for each function call. However, if a function is static, all the variables inside the function are shared across different invocations of the function that are running concurrently. A function must return a value. However, if you notice the syntax, there is no declaration of the return variable. Typically, the function name itself acts as a return variable. Functions are limited to returning only one single value. Functions should have at least one input argument, but they cannot have output or in-out arguments. Functions do not include time delays. For example, hash or event control statements like @positive edge or @negative edge. This means that the functions are executed in zero time delay. They are used to implement purely combinational logic. A function cannot call a task inside it, as the task may consume simulation time, but it can call other functions. Verilog functions are the best way to implement simple combinational logic that can be evaluated instantly, for example, arithmetic operation or logical computations. Now, let's discuss what a task in Verilog is. A task in Verilog is a reusable piece of code that takes input arguments, performs operation on those arguments based on given statements, and outputs one or more output arguments. A task can perform more complex operation compared to the function. Let's look at the syntax. A task begins with keyword task and ends with keyword end task. The inputs and outputs are declared after the keyword task. If there are any local variables, those are declared after the input and outputs. Similar to a function in Verilog, a task can be static or automatic. If a task is static, the variables inside the task are shared between different task invocations. While if it is automatic, the variables inside the task are not shared between the invocations and dynamically allocated for each task call. Tasks can have timing delays, for example, hash or event control, like @positive edge or @negative edge. It can also contain blocking statements like wait and fork join. Task can have any number of input and outputs. A task doesn't return a value. However, it can set multiple outputs using output argument. A task can include another task and functions inside itself. Tasks in Verilog are suitable for operations that are complex, require delays, or need to pass multiple values. For example, stimulus generation. Now that we understand a Verilog function and a Verilog task construct, here is a summary of the differences between the two. Function cannot have delays or time event control statements, while a task can contain these time control statements. Function can return a single value. A task does not return a value but can set output in one or more output arguments. A function cannot call a Verilog task inside it. However, a task can call other tasks and functions inside it. A function must have one or more input arguments but cannot have output or in-out argument. While a task can have zero or more input, output, or in-out arguments. I hope this video helps clarify these concepts commonly asked in interviews.